welcome to the 2020 Brain and Transcranial Photobiomodulation Virtual Summit. I'm your host, Dr. Joe Doduro, and my guest is Tyrell Pruitt. He's working at the University of Texas Arlington. He got his MS there from UTA. He's had his BS in pre-medical biology from Tarleton State University. He has spent the last 5 years working in the lab of Hanli Liu, expressing his expertise in these topics of medical imaging. And he won the Most Incredible Adolescent in Texas Award because as a cancer survivor, he was still able to go on with his schooling, and he will complete his PhD in about 3 months. Thank you for your participation here today.
Glad to be here. Thank you for having me.
One of the things that we want to look at is when you started your pre-med and everything like that, and what path did you take to get to see the light, if you will, to get into photobiomodulation?
Gotcha. So it's a weird path. So of course, going into pre-med biology, you would think I would want to be a doctor. But I received a math minor, and I thought, because of all the stuff I went through as a kid, the actual devices and things like that interested me more than the medicine itself. So treating the problems of the future rather than the problems today. Okay. Yes. So whenever I went to UTA, actually, my MS is in a specialty of tissue engineering. But towards the end of that career, I took a few courses from Dr. Hanli Liu and learned about her research, and it was very promising and astounding research. And I had the biology expertise to add to the lab. So that is how I started, 5 years ago, and saw the light. And from there, I worked at both UTA and UT Southwestern in a collaboration project to study both the effect of light on the elderly as well as healthy normal controls. Dr.
Hanli Liu has just been so inspirational and so, created so much positive information, and she has a great lab and great people working for her. That's why I'm so glad that we were able to highlight the research that's coming out of there and the people that do it, because it doesn't get done without the grunts,
Right, exactly, like me.
So when you first heard about photobiomodulation, and in Hanli's lab, it's mostly transcranial at this point, what did you think? What did you think?
Well, to be honest, at first, it was very hard to believe. At first, I wanted to make sure that it was real at all, because some of the effects are, they're very subtle yet quite profound at the same time. So whenever I first started, I really wanted to confirm what we were seeing in a quantifiable way. So that's what I wanted to bring to the table, is being able to actually quantify these effects, both to metabolism and to EEG signals as well.
Well, if I can, ask you a personal question. I mean, you're looking at the brain, and do you have any, personal experience with brain?
Whenever I was doing pre-med biology, I studied a lot of biochemistry and things like that. But before working in the lab, really, all I had experience with was that biochemistry. So looking at it on a cellular level first, before the macro level, was very important to me.
That's excellent. That's excellent. Let's go to the slides. Let's go to the video, Jim. So we're looking at transcranial photobiomodulation with 1064 nanometer laser to improve cerebral metabolism of the human brain in vivo. Go for it.
So that is kind of a mouthful. So hopefully I can break it down in a way that everyone can understand. So first, about my background, I've worked 5 years now, should be receiving my PhD soon, as Taylor already said. And my specialty is in BB NIRS recording as well as EEG data analysis currently. So my perspectives on TPBM that it is a very promising field. So my background and expertise on the subject is, of course, I've worked in this lab for 5 years in collaboration with both UT Southwestern and UTA. My specialty at the moment is BB NIRS data recording, so actually recording the cellular and metabolism data of transcranial infrared brain stimulation in vivo using this technology, as well as EEG data analysis. So recording the electrical signals of the brain as well and seeing what is happening, what does it mean. So my perspectives on TPBM is that it's a very promising field. From my research alone, it appears to not only be very reliable in healthy normal controls, but as well as the individuals of higher age and possibly even disease states. And it appears to be a uniform effect across everyone, which is quite remarkable. So I think that there's great promise in the field of TPBM. Okay, so in order to reinforce this fact, I'd like to move on to my research information. So you know, I know what I'm talking about. So light stimulation. So how do we do it in the lab? So we use this handy 1064 continuous wave laser. So what this allows us to do is actually have a handheld 1064 light to stimulate the brain. So we operate it at about 3.5 watts, and it allows this light to actually go through the skull and into the outer cortex. So by using this simple device, almost like a flashlight, you can think of it as, we can just hold it in front of your head, with protective goggles, of course, and see these effects. And it's non-invasive, and usually the person can't feel anything is happening at all. So it's very, very cool in my opinion. So this would be how we would measure this BB NIRS effect, or the metabolism. So you can see there's about a light size of about 4 centimeters. So that light will hit your forehead, and then we pass a light from the source to the detector. So from that source to detector, we can get all the information in between. So you can imagine it kind of like a banana of light is how we normally like to call it in this field, where we're getting the average data in between this source and detector.
You can use your mouse to kind of point out stuff too.
Oh, yes, yes. Yes. So you can see here is the source, and as it passes through here, it will intercept the area that's being stimulated by the light. And then once it gets to this detector, we can detect if any changes have happened along the way. So while the person is at rest, we would measure them with this device to get a reference point, and then we will either stimulate them with the real light or sham stimulation in order to have a...
My question is that how are you doing this just to show a picture, or is that how far the light is off of the head?
Oh, yes. So as I point out in the caption at the bottom, the light is normally much closer, so 2 centimeters. So this is just to capture a good shot of the head. Gotcha. But the light will remain the same diameter on the head. It'll just be much closer.
Very good.
And so as the light stimulates the person, things will change, and we can detect those changes. So normally what we will do, this is our pretty much universal protocol at this point. We would have a 2-minute baseline where you're just sitting there and you relax. And then we're measuring the whole time. And then at the 2-minute mark, we will begin 50 seconds of light stimulation. And after those 50 seconds, the laser will stop and will acquire for the next 10 seconds. And so this gives us 8 good data points during this time. And afterwards, we measure the post-stimulation effect to see if it's still happening after we stop the light. Normally, we can actually still see that effect for many minutes after. So we continue that process for 5 minutes at least. So overall, the protocol is very simple. It takes less than 30 minutes for a person to come in and get a measurement. And, they're in and out the door. And so in an hour, we can have both a sham state and a real stimulation state as well. Of course, on separate days, usually a week apart, to stagger them because we don't want any overlap. That's very important. So what we can see here is kind of how this works is as the light passes through, things block the light from source to detector. So you can imagine if there's more blood in between one end of this detector and the other, then more light will be absorbed unless we get to the detector. That's the very basic principle of how this works.
Of BBNRI NIRS, NIRS.
Yes, which stands for broadband NIRS.
There you go.
This is essentially just a small flashlight. It's a very intense flashlight, but it is normal white light. But by shining this from one source to the other, we can measure all the kind of wavelengths of visible light at once. So that is why this technology for broadband NIRS is much more accurate to the cellular level than, say, functional NIRS.
Oh.
Because functional NIRS only uses 3 wavelengths, whereas this would have an entire spectrum of wavelengths.
That's probably going to be important to do something, but instead of being, why does the light go from the source to the detector? Why doesn't the light from the source just kind of make a fan?
It does. So we only capture a fraction of what actually comes out.
Oh.
So that's why it's important to have a very high intensity light as well as a very measurable effect.
You know, the one thing I think most of the researchers say, I was skeptical at the beginning about this photobiomodulation. And the more you look at it, you're like, wait a minute. Light is going through the head? I mean, what? I mean, that's the first thing. And here we got kind of 2 different kinds of light going through the head. We're using actually light through the head to measure light through the head. So I mean,
yes,
that's an interesting point that, it's like, well, yeah, I guess light does get through the head, So.
Yeah, so it is quite unusual, which is why we don't have them turned on at the same time. So that's very important. And something I'd like to stress, if anyone else wants to do a measurement like this, is that having both on at the same time will, of course, provide interference. So it's very important that we have this kind of threaded or interweaved acquisition method.
Quite elegant.
Yes. So as more light is blocked, we can see if the oxygenation of the blood changes, if deoxy blood is increased in the local area. And the real novel thing about this is we can actually see cellular activity, which is cytochrome C oxidase. So cytochrome C oxidase is on your mitochondria actually, but it has a tiny copper subunit, almost like a very small penny, that this light can hit and actually absorbs light at a very specific wavelength. So by measuring when it binds to oxygen, so one more photon, let's say, gets absorbed, we can see if it's activated or not, or oxidized, rather. So that is the beauty of this broadband NIRS technology, is we can measure these changes. And so I would like to move on then to what we actually measure, because I'm sure that's what most people are here for. So on the left, we can see oxy blood. So we acquire every minute for 13 minutes after baseline. and the areas in red are the areas of stimulation. Now, what makes these graphs important is that they were taken 2 years apart, and they were taken at different locations with different equipment. So completely different personnel, equipment, and location, but the results have no significant difference between the two.
Well, my question, Tyrell, is these aren't the same students or young adults.
No, so they are 15 separate individuals from the 11 measured in the first study. So on average, the effects of the light are very consistent. So this proves that not only are the effects of the light reliable, but they're very consistent. So it doesn't matter.
Even if you look at the variation of the measures, I mean, not only is the measure pretty close, but the variations of the measures are very close, you know?
Exactly. So this method of acquisition and the actual light stimulation are almost constant, you could say. This effect is almost always happening. There is the occasional outlier, but even 2 years apart, different individuals, different equipment, the exact same rate of change and type of change can be seen in these two graphs with no significant difference between the two.
That's a great study.
Yes, but what is even more exciting is the two age groups. So what we can see here is I believe the solid line is, let's see. Yeah, so the solid lines are the young adults, so individuals younger than 55, and the dotted lines are older individuals who are 55 plus. So these, this data was taken at UT Southwestern Medical Center, and you can see that there is some significant difference between the two, but there are consistent differences. So the older adults, at least in baseline, show an increase in HBO regardless, and the young adults do not show this increase. So we think that there is some difference between the hemodynamics of the two groups. So as an older person is sitting there, they just naturally get an increase of this HBO and get a decrease of their mitochondrial function.
Very interesting. So let's review this again. The dotted lines are the older people.
Yes.
And there's on those little stars, those are at the times when it's significantly different. The amount of oxygenated blood that's passing or being utilized, which is at the concentration of the blood. So it's more oxygen is being delivered to that area, right?
Yes. So regardless of the age group, there is an increase, but from the point of baseline, so that's delta concentration or the change in concentration. Okay. From that baseline point, there is still an increase, but it's not as high, one would think. But you'll notice that their baseline is also lower. So taking this into account, we can then move to this figure, which
Can we go back one? I wanted a question on the CoQ10 oxidation one. The concentration of that one, that seems to kind of go down. Because we're looking at the blue is still the sham though, right?
Yes, so the blue is the sham. Yes, sir.
So the older sham went down, and the old man, I won't say old man, the old man sham, the old man treatment went up, but it was a lot different than the young person in the CoQ10 aspect. That's what I see, right?
Oh yeah, so cytochrome C oxidase, the CCO on the mitochondria, it shows an increase, but it's not as high as the young person's. So you would think, but because they're placebo, or when they're just resting, so during sham stimulation, it's decreasing. So if you look at the actual difference between, say, this point and this point, the next figure shows that they're actually the same.
I thought you were going to get there. Go ahead. Go ahead. I just want to set you up there. Get a slow pitch. Go ahead.
Thank you. Thanks for the setup. But regardless, there is still an increase from baseline. So that is very important. It means that this not only affects people with healthy young cells, but also older, more aged cells. And from this figure, we can see that when we account for this, so we subtract the placebo or sham from the stimulation measurements for both groups, that they are almost identical. So there isn't any significant difference between the two groups now. So from this, we can say that on a net change perspective, that the light stimulation is just as effective on older participants as it is on the younger. So this is a pretty surprising finding, in my opinion, because we went into this thinking that the light would have much different effects on an older individual than the younger, because the vascular system and things like that are much different as one ages. But what we found was that the light produces a change that is almost exactly the same. So this makes light stimulation very promising for treating diseases that normally affect the people that are advanced in age, such as, say, Alzheimer's and things like that.
One question, Tyrell, is this: you would think that the mitochondria of the older person is going to be somewhat compromised. Yeah, you didn't see that in a particular. After you age 30, you're going to lose 10% of your mitochondria every year.
Right.
So if you got a 50-year-old person, you would expect some difference, you know?
Right. So there is in the non-net corrected. So as a person sits there as the older people, you'll see that their actual CCO function decreases as they're at rest. But the actual change of the light from this decreased state to their stimulated state is equal in the amount of change.
So let's say this a different way. See if we've got this right.
Okay.
You may have less mitochondria, but they are activated in a similar manner.
Yes. Yes. So although there are less mitochondria, the light still stimulates them in the same manner of a young person, let's say.
There you go.
So yes, as I said, this is very promising, and the treatment aspect that eventually TPBM wants to move into, that there is a measurable effect on the older population as well as healthy people.
Cool.
So how do we confirm these findings, let's say? How do we know that this light is actually getting to the brain and we're not just measuring things close to the surface? So how do we confirm this? So what we're currently working on in the lab now is we've published in these conference papers, is we're using phantom analogs to actually measure the amount of light that's delivered to different parts of the brain, theoretically. So we adjust the conditions in our phantom and then use the same spectrometer we use for broadband nears to detect how many photons are getting to a particular position.
Ooh.
Yes.
So what I see your setup is here is you move the stage, the blue L, further away and take different measurements, huh?
Yes, exactly.
Brilliant.
Yes. So this is a way that we can set up the conditions, let's say either more scattering or more absorber, just like you would see in tissue or the brain, different tissues.
Wow.
And an easy to use or an easy to move through liquid scenario, and then use this to detect exactly how many photons are reaching a particular point.
So you can make it thicker. You can make it more viscous. You can make it like a bone, like not a bone, but you can make it like a blood, like a cortex, like a gray matter. You know what I mean? Keep moving it down, brown, white matter. It just and vary the distance with every time you vary the substance, right?
Exactly.
Wow.
Exactly.
Well, you know what? It's like Christmas time because I've been waiting for somebody to do this for a long time.
Yes. So this is our current research. This is we've already presented this at multiple conferences. So hopefully, but this is some of our preliminary promising results. So by using these experimentally collected data along with theoretical calculations, we can predict based on certain conditions exactly how many photons will reach a certain depth by using predictive models and things like that. So you can see the dots and symbols on this figure here are our experimentally collected data, whereas the line is the theoretical calculation.
Look at that. Look at that.
Yes, exactly. So this theoretical calculation that we've come up with almost exactly matches these experimentally calculated dots. So hopefully, by further refining this, we can determine exactly how much a dosage of light is reaching the cortex in deeper parts of the brain.
So are you going to tell us a little bit about what kind of light and what kind of distance that you found?
Oh, yes. So with this is all using 1064 nanometer light, just like was used in the previous paper. So we found that 1064 light actually penetrates enough to reach the cortex. We can say that. So it definitely reaches the cortex in depth-wise, but we still need to explore further on the radial measurements and things like that.
Oh, so if I'm not mistaken, the normalized fluency, would that be almost like a percentage? Could we say that like 80%?
Yes.
So at 1 centimeter distance depth in said tissue, whatever tissue you're using here,
yes,
you had 60% of the red line, but the green line at 60% went a centimeter and a half, and the blue line at 60% went almost 2 centimeters deep.
Yes. So what those colors represent, without giving too much away, is aperture size. Yes. So I know. Thank you for the setup. So those the different colors represent aperture size. So the smaller the aperture, the less distance it penetrates. So you can imagine the red line would be a much smaller aperture than the green and blue.
I got you. So you're kind of going to centimeter squared aspect, right?
Yes, exactly.
So the fluence or the fluency, that's what it depends on, the centimeter squared aspect, right?
Yes, yes.
That's good. That's good. That's good. And I am the moderator.
Yeah, so very promising results. So we can say that this light is definitely reaching the cortex, and that is most likely what we are measuring in these other measurements as well. So from there, how do we see exactly what's going on the macro scale? So then we move on to this diagram. So for our EEG studies, we use the same 2-minute baseline, 8-minute stimulation, 5-minute post-stimulation period. But of course, we have the person hooked up to an EEG. So using this technology, we can measure the actual electrical signals that are coming through the scalp.
Mm-hmm. And the blood.
Not blood. So
this one doesn't have the blood. This is just
exactly.
I got you. But
so they have to be measured separately currently.
So what you're saying is you've got all the data from the blood, old, young, reproducible, placebo. We got all that. So now let's use the exact same reproducible stuff and see what's happening in the brain electrically.
Exactly. So we go from the micro to the macro scale. And this is what I was talking about that was important earlier, is going from the actual metabolism aspect, measuring it quantifiably what's happening. So we can say that HBO is increasing, as well as the mitochondrial metabolism aspect with CCO. So now that we know that these things are happening, what are they actually doing to the brain? And this is what we can measure with EEG.
Like it.
So what we've measured in the past, my colleague Dr. Jinlong Wang in biophotonics published this figure. So we can see that both alpha and beta have increased, or they show significant increase. But what is unusual is that from the TMAP, you can actually see that at least in beta, there's actually less around the actual site of stimulation, which is confusing.
So let's just give people a little pointer there. We're looking at the
oh yes, sorry.
TMAP, and this is T is greater than 3.6 in the yellow, and T is equals to, what is that? What is this TMAP bar?
Yes. So this TMAP here it kind of designates where there's a significant change in the signals that we see. And from these other maps, so this indicates a T of less than 3.6, and this is greater than, which is the yellow and the blue.
Okay.
Yes. So in each of these is a different minute as well. So you can see at minute 8, this would be the information for minute 8, whereas this would be the information for minute 1.
I got you. So the T maps are the blue ones, and the red and the red to blue is what?
Yes. So the red to blue are the mean, and the lower these are only the areas of significant difference from the TMAPs. So you can imagine ES is a combination of the first two.
Thank you for that. Thank you for that.
So a little bit easier to decipher now. So
let's let everybody know when we're looking at this thing in the upside down reverse. In the beta, on the second line at 1 minute, the R spot right there, that's about where you put the laser.
Yes.
So, and then in all areas, that's the area that the laser is being applied.
Yes. So it's always being applied to that particular electrode in that area.
Got you. Now, when we're looking at this, just from my perspective, as I go down that 1 minute mark, I see a lot of red there in the back. That's the 8 minute mark now. I can see a lot of red in the back of the head.
Yes. So we see a lot of alpha being generated and beta being generated in the actual back portions of the head. So why is it not coming from the front? Because surely that is the area of stimulation. So we need to look further into that to determine why that is happening. So by doing a simple power analysis like we had done here, we can't really get all of those answers.
So I appreciate that. Let's go back to the beta TMAP. This is a little less I start to turn on the laser at 1 minute, 2 minutes, 4 minutes. I get in a hot spot, maybe at the end of it, like a pool ball. It's going from the front to the back.
Yes.
It's bouncing off the back, boom, 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 and it's getting hot. Let's just say more active up until 11 minutes. Then it kind of cools off. Then it kind of shoots up again in the relaxed phase, right?
Yes. And during this whole time, the laser is continuously stimulating the brain.
Until the relaxed time.
Yes.
So the thing it's really pretty amazing. You showed that your laser at this point has the ability to penetrate 2 centimeters and give a significant dose, right?
Right, yes.
So what do you think the distance is from the front of the head to the back of the head back there? How far do you think that is?
More than 2 centimeters, I will say that.
So, I mean, the question comes,
what's happening?
Yeah,
exactly.
I like that part when we talk about then a miracle happens and we go to the rest of it. Something happens and then we go, tell me about that.
Yes. So from this perspective, you would say that, you stimulate the front part of the brain, question mark, question mark, question mark. Then all of a sudden, profit, you have the signal at the back of the head.
Right.
So while we can't definitively say what is happening currently, we have done some additional analysis since this time using various different methods. My colleague, Dr. Zhilong Wang, is also doing some research on this. But for my own personal papers that we presented at OSA last week, not to date this, there is a significant change in the actual flow of information. So this is that connection that we're looking for. So you can see it's kind of hard to see, but these arrows kind of, so the same stimulation site, the same data actually. So from 19 individuals from the previous paper, you can see that although the site of stimulation is there's a lot of information flowing front and back. There's a lot of communication that isn't present in your placebo or your sham.
There's a placebo over there.
Yes. So you can see no lines up front, placebo, tons of lines up front and on the left side actually in stimulation.
So, we can, the point may be, there may be some quote unquote perception of the source that's going to the detector in the placebo. You may having some activity from the source there because we have some kind of activity in the back in the placebo.
Yes. So these areas of the brain are communicating with each other. And not to give too much away, but there is definitely strong connections that we can't see in the power map of, say, signals appearing in one area of the brain and then traveling to another. Mm-hmm. So what you're seeing from these lines is, let's say that there is a signal coming from AFZ here.
Right.
That's not a good example. Let's say from the back here, that is then appearing here. So as you lag these signals in time, the same signal appears later in these areas, which indicates that there's a high probability that there is communication between these 2 points of the brain. So this communication only happens during light stimulation. So those signals that we're seeing in the back could be due to this communication aspect from the front.
So what you're saying is that you see that I see because what I'm looking at here, I see some of the arrows are going from the front to the back, but some of the arrows are going from the back to the front. Correct?
Yes. So it's communications both ways.
And let me ask you this: this is just a surface map of the communication, or are you able to read deeper talking that's going back and forth?
Well, okay, so that is going to be elaborated on further in this manuscript, hopefully. So not to give too much away once again, but, possibly. But the problem here is that without high definition EEG, these signals are very hard to kind of decipher using this method. So this is a normal 64 electrode cap or low density.
Mm-hmm. So one of the things that I heard about EEG or reading electrical activity off the brain, they made it into like, the best one I heard is like putting microphones, and then listening to a stadium full of people, right? And then trying to figure out what one guy is talking to another guy. What are they saying?
Yes.
So it gets more complex as you try to go through all the noise to hear what's happening in the little section, correct? Is that?
Yes. So essentially what we're saying here is one guy with a megaphone is trying to talk to a specific person on the other side of the stadium. And that communication is occurring. So all of these signals are happening, and we're kind of sifting through it to find these points that match.
And what by saying points, you're looking at it, I mean, how is the movement? Because this interprets as that the electrical activity is going like this. Is that correct? Or are you saying this is a signal? And what is it? How do you pick up the other signal? Because I'm relating it to it is you're watching that ripple or that electrical thing go across over here. Am I wrong?
No, so not technically. So remember that with EEG, we can only detect the surface signals from the cortex. So these signals could be either traveling deeper into the brain, or they could be changing on their way to the other point. So the way we actually detect this and plot the arrows is you take one signal and you analyze all the other signals, so the whole stadium at a later time. And so using this, we can find Waldo again in the stadium and say that, oh, these 2 points have matched, but they're later. So by using that, we can determine this directionality of this signal has traveled here, but we can't plot the whole way or the whole journey.
Decipher. You don't know what he's saying.
What was that?
He's shouting out. You can hear him yelling. And
yes, but we don't know what he's saying. Exactly.
Don't know what he's saying yet. But that's going to come in the publication. I know.
Yeah. Later.
Oh, tune in next time. I got you. But my question is this. Are you going to look at this topographically in a sense? Because a lot of the presenters have talked about connectivity and patterns, and maybe even communication fasciculi that are underpowered or not working and things like that. I mean, I know there's programs and there's math, that can run all this stuff. I mean, do these things, are they just random, or are they going along certain paths? Can we say that there is a fasciculi that travels from like T something to T something else, T odd to T even, and can we call that we saw it moving on this track?
Well, what I will say is that this data was tested against 1,000 surrogate random data sets. So it's sometimes known as bootstrapping. So the computer generates 1,000 random data sets and then compares that to what we see experimentally. So using this rather rigorous kind of statistical testing, it's probably the most stringent to my knowledge currently. We can determine that this isn't just some random noise, but rather this is the almost exact same signal that's appearing elsewhere, and put a probability to that. So although we can't say for certain, we can use this math. Let's say these red lines here, those can be estimated with around 70% certainty. So although I can't say 100% that these signals are directly linked, no one really can, but I can say with 70% certainty that they are.
That they exist and they're moving in that direction.
Exactly. So by combining it with the power diagrams you saw earlier, so we know that these signals are happening, they're increasing, and then linking them to the signal traveling, then we can say, okay, maybe there's something happening here. But of course, there's always more research that needs to be done.
Stay tuned. So my question about the anatomy of this machine. What is it? Are there any things that are, I mean, we can't really say at the surface because the interconnection in the cortical top part doesn't really go that far. You have to go through the corpus callosum to go from odd to even, right?
Yes, correct. So we can't see what's actually happening at that deep level currently, because EEG only gives us a surface level. So we hope to kind of catch the signal as it starts and then catch it on the other end. And then we know that those 2 points are communicating, but we can't map the direct path yet currently.
I like it. I like it. You got any more slides?
Not currently. So now I believe this is probably the end of the talk that I currently have.
Okay. You probably got some, but you'd have to have, I don't have the clearance for that. I understand. So I want to thank you. I mean, you grew up in Texas. You're born and bred in Texas?
Yes, sir.
You do your best to keep that accent at a minimum. I only caught it a couple times. So thank you. And, you know, there's a lot of stuff that you are part of a huge facility that's bringing this information forward at a very rapid rate. You have a great team. And I kind of want to say, I mean, you have only been in this a couple of years. I know we had researchers doing this for 30, 40, even 50 years of their life's work. So you may not have much posterior, you know, perspective, but tell me about what you see happening in the future. What do you see at the 2030 brain and transcranial photobiomodulation virtual conference? What are we going to be talking about then? What research are you going to have?
I think that we're absolutely in the next few years going to see more research being funded for disease states. So rather using light to actually influence a person with, say, Alzheimer's or things like that, to try and provide some kind of treatment, or at least in a higher capacity than we are currently. And hopefully by that time, we'll know more about the actual mechanisms behind TPBM, because every day we're learning something new. So hopefully, I imagine by that time, we'll have at least most of the answers.
Those question marks and be fill in the blank. You're going to work on filling in the blanks, right?
Exactly.
And thank you, Tyrell. Thank you so much for your time and your great work. And I'd say thank you to everybody in the lab, too. We really appreciate your participation and the hard work that you guys are putting in there.
Yes, thank you. Thank you for allowing me to come on and talk.